And hopefully you're back. What we're going to talk about today is a more in-depth conversation about sorting than what you had in your last class in 161. And in 161, we made mention of the selection sort, the exchange sort, and the insertion sort. And we really didn't do anything with the insertion sort. But these three, selection, exchange, and insertion, are generic thoughts of how to do sorting. And we're going to use these basic concepts, and we're going to start getting into some other sorts that use the concept but are more efficient than what we had. Going back to 161, we had the selection sort. And let's see if any of you remember, you turned the program in about this time of the semester, and it had 4 different sorts in. One was called the bubble, one was called the Dan, one was called the selection sort, and one was called the shell sort, where I gave you a flow chart and you had to come up with the sort from there. Taking a look at a quick review of what the selection sort was, we took a list, an array of numbers, and we wanted to sort them. We could have sorted them either ascending from low to high or descending from high to low. It's like you descend down a hill. You start high and you go low, or you ascend up a hill. And the first sort that we have on this list is the selection sort. And I don't know if you remember back or not, but we went through the whole array, selected a number, and then put it in its proper spot. So if you took a look at what we have here, and I wanted to sort this array ascendingly, I would start and I want to fill the first column. I want to fill this first one. So I'm going to start here, and I needed to find what was the smallest number. Right now, 8's the smallest number, right? Yeah. I moved to it. No, wait, 3 would be smaller than 8. So now 3 is the smallest number. 6 is not smaller than 3. 7 is not smaller than 3. 9 is not smaller than 3. 10 is not smaller than 3. 1 is smaller than 3. So we now needed this location and this value. So what would I do? I would take the 1 and its location and swap it with the 8 and the first location. So this became a 1, and this guy now became an 8. Then I moved to the second spot. Okay, what's going on here? I'm going to do the same thing. So I'm going through the array one at a time, all the way to next to the last. And then once I get in, I'm going to start here to find the smallest. So my next thing would be to go through, and I would actually swap the 3 with the last location. So the 2 moves into this spot, the 3 moves into that spot. Okay, we're going through, we're selecting a value, and we're moving that particular value. If I went through the array again, I would get the 3, and the 6 would move to this spot. And I would keep going on and on and on. Anybody know big O notation for this one? What would it be? How many loops do I have? Can you hear me?
O-N.
Okay. If I had 1 loop, it would be O of N. But what do I have here?
Square.
Yeah. It's not constant. It's not linear. It involves going to every spot anyhow. So I'm guessing that's the
O of N squared?
No, not even n factorial.
Nope.
Maybe O(n) squared, yeah.
Yep, that's what it would be. Going through the loop twice, it would be a big O of N squared. Okay, does everybody remember the idea now of what the selection sort is? I select a value and move it. Exchange sort. This one was the bubble sort. And if you remember to the bubble sort, this is one where we went through and we took a look at the first two. Are they in order? The answer would be no. So I would exchange 3 and 8. Then I'd compare 8 and 6. Are they in order? No. So I swap those. I compare 8 and 7. No. So I swap those. I compare 8 and 9. They're fine. I compare 9 and 10. They're fine. I compare 10 and 1. I have to swap them. I compare 10 and 2, and I have to swap them. Now, when we learned the bubble sort, we went through that process of exchanging. And then I said, oh, did I make any swaps? The answer was yes. So I went through and did it again. 3 and 6, these are fine, these are fine. 9 and 1 would need swapped. 2 and 9 would need swapped. Did I make a swap? Yep, go through it again. So I have a loop going through and then an outer loop that was a while loop to keep me going again. This was the bubble, similar to the Dan sort because we were doing exchanges. But once again, the bubble, because it's a loop inside of loop, has big O notation of n squared. Okay. The last sort was one we didn't really talk about in 161. And if I draw a quick array and I start saying, all right, well, what's the insertion sort? Anybody remember when we discussed this, what the insertion sort was? We didn't work with it. We only discussed it. Okay, well, the insertion sort was one where instead of filling the array first with 8, 3, 6, 7, 9, 10, 1, and 2, as I inserted them, I put them in order. So the first number was the 8. I put the 8 in. It's like a deck of cards. So if I'm making notes down here, I'm going to put deck of cards. You know, when you're playing cards, as you get the value, you put it in. Now, my next number is 3. Where would the 3 go? Well, the 3 is less than the 8. It would go in front of it, right? This isn't so good because I now need to shift things over. But being the smart, intelligent folks you are, all of a sudden I hear you say, well, you know what? Instead of an array, maybe we should be using a linked list. Now, if I go to put in 3, I create a new node. Head goes to 3, 3 goes to 8. My next number was 6. Head goes to 3. 3 would go to the new node 6. 6 would go to 8. So I think I had something for inserting into a linked list that would actually work better than working with an array. Would all the values be sorted? Yes. Do I insert as I go through? Yes. Worst case scenario, the numbers are already high to low, and I'd have to keep bumping everything or going to the end to add things if they were already sorted ascendingly. Okay. So we have the 3 basic concepts. Sounds like a test question. Selection sort, the exchange sort, and the insertion sort. Now, what we're going to do in the next couple of sections is we're going to look at variations of these 3 that use the concept select and move, or exchange, or insert. That is going to be a faster way of sorting. And the first one we're going to talk about is something called the heap sort, and it's a type of selection sort. Now, in order to do the heap sort is going to use a binary tree, not a binary search tree, but just a binary tree. And when we do this, we're going to get big O notation that looks like big O n log n. And we'll talk about that if we have time at the end. But here's what a heap sort does. We need to, first of all, start by defining what a heap sort is. And again, this is NIAF chapter 13. So if you're following along in the book, it would be good to have. What is a heap sort? Well, a heap sort, I'm going to give you the overview, is first of all to have a binary search tree. 11, 6, 8, 2, 1, and 5. Okay, so I have a binary tree. That's all I need to know is a binary tree. This binary tree has to have a couple of things going for it. The first one is it has to be complete. And what I mean by that is it's filled in by row from left to right. So this guy would in fact be complete. The second thing is the parent has to be greater than the children. Now, we would be thinking, well, that 5 should be over with the 6 and over here. And don't think that way, okay? Don't think that way. You're going back to a binary search tree. This is a heap sort. And what's going to happen is we're going to learn the heap sort, but we're actually going to use an array later. Now, this idea that it's complete, boom, 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 boom. Remember when we filled in an array with a binary search tree, we had a lot of blanks. But this guy, 0, 1, 2, 3, 4, 5, is only going to fill an array of size 6. I'm not going to have any wasted memory, and I'm not going to run out of memory. All right? So in order to have a heap sort, the first thing I need to have is a heap. This guy is a heap. It's complete, and its parents are bigger than its children. Okay, staying on the topic of the array, we did this the other day. We took a look at where's the parent and where's the children. And we had formulas that went along with this. The parent, oh boy, this was 0, 1, 2, 3, 4, and 5. And does anybody recall what the formula was for where's the parent? So if I have 3 and 4, where's the parent at? Good. N minus 1 divided by 2. You say 3, I get 1. You say 4, I get 1. Does anybody remember where the 2 children are? Going to be close to this.
So 2n plus 1, 2n plus 2.
Thank you. So when I'm looking in an array, if I have the array of elements and I wrote this array out, 11, 6, 8, 2, 1, 5. And I wanted to know where the parent was for 5, I would look at the subscripts, 0, 1, 2, 3, 4, and 5, and say its parent is at 2, 0, 1, 2, the parent should be at 8. Okay, so we're going to keep that in mind, but in order to learn how to deal with this array for the heap sort, I'm going to draw it using a heap. Some of you say, well, why not use a binary tree? Well, once we get the concept here, the array is going to become a whole lot easier. Okay, so I'm looking at a list of things that we need to do, and one is to insert. You know, I want to be able to insert to get things up and running. You know, I always know I need to find the, is it empty or not, you know, and save some time with that. I want to be able to get the largest. Where's the largest at? Where will the largest always be at? Won't it always be up? Yeah, it's going to
Towards
be
the
at the
right.
top parent. So that I need to be able to get the largest. So it's going to be, some sort of get largest, which is always going to be the root. But what happens if I remove the largest?
But before you remove, like, what if the first element in an unsorted list is like 2? Wouldn't the largest be to the furthest right?
Well, what's going to happen is I always want to have a heap. So if I so as you see in a couple of minutes, what's coming up, we're going to work with these ideas. But here's a heap, okay? And the heap, by definition, this is an example. So what we're going to do in a minute is we're going to build a heap, and then we'll see how to sort it, okay?
So basically, we first have to find out what number is the largest from the list,
Right.
and then you pull that number to the front, and then you build a binary tree. Okay.
Right. Let's start with that. Okay. So let's start with insert. And I'm just going to put a dummy tree up here, and then we're going to insert it. I want to make sure that it's complete, and I want to make sure that it is up. Well, let's start with a list of numbers. 6, 9, 12, 4, 2,
7.
and 3, and 7. Okay? So the first thing I'm going to do is say, all right, 6, you're the winner. You're at the top. The next number I'd like to add is 9. So here's the 6, here's a 9, and
To the right.
well, no, it's not going to. See, you're back to thinking binary search tree. So I don't want you to think that way. Remember, this has to be complete. So when I insert, I'm going to insert the next row left to right. So when I put the 9 in, I hit this spot. But now a new term pops into mind. When I go to insert a new item into the list, I need to say, wait, its parent is smaller, so I need to switch it. This idea is called percolate up. And if I percolate up, 9 is now at the top and 6 is here. Next number I'd like to add is 12. Again, I'm adding from left to right. What's the matter here? I need to percolate up. So 12 is going to switch with 9. I'm back to being complete, and I'm back to being heap. Next number I'm going to insert is a 4. Do I have to percolate up? Say no.
Nope.
Nope. Okay. The next number is a 2, 6, 4, 2. Do I have to percolate up? The answer is no. The next number is a 3. Oh, I was going to say I forgot something there. There's my 9. Actually, it's a 13. So now I'm going to put in 12, 6, 4, 2, 9, and 13. Now, where do I have to go with the 13?
Swap it with
Percolate up.
Up to the 9 spot, and then where?
To the 12.
Up to the 12. So now I'm going to have 13. This left tree stays the same. There's 6, there's 4, and there's 2. The 13 moved all the way up, so it switched with the 9, and then it switched with the 12, and I have something that looks like this. Last number is the 7. I put in check, and I don't need to percolate up. So whenever I want to add an item, I need to see if I have to percolate up. So that's my first term, percolate up. Okie doke. So far, so good?
Yes.
All right. Now, the next thing I want to do is say I have my tree, which we see right here, and I say, okay, I want to get ready to sort, and all I really know right now is that 13 is the largest number. So if I'm sorting in ascending order, that's my last number. If I'm sorting descending wise, that would be my first number. So if I'm thinking of this as an array, I have 13, 6, 12, 4, 2, 9, and 7. All I know out of this array is this is the largest number. Agreed? So if I say, okay, let's take this number and it should go at the end. So I'm selecting a value. Remember, I said this is a type of selection sort, and I'm going to swap it with the last thing at the, I want to remove the 13. It's gone. Okay. When I remove it, I'm going to swap it because I want to put it in that spot. So I'm going to remove the 13. And when I do, I get a new heap that looks like this because I removed the 13. Now what's my problem? Do I actually have a heap?
No.
No.
Because
Right?
12 is larger than 7.
Yeah. So which way should the 7 go? And what's the term I'm going to use?
Percolate down.
Yeah, I'm going to percolate down. Seven, which way will the 7 go, or does it matter?
The right.
To the right. Why?
The text 12 is bigger than it.
Yeah, well, yeah, what if this number was bigger than it? What if this was a 9 instead of a 6? Remember what we want. We want the parent to be larger than both children. So what I'm going to do is select the largest here and move it up. So now I would have 12, 6, 7, 4, 2, and 9. Are we happy?
And the 2 and the 4, the children of 6, it doesn't matter, right? Like,
It does
because
not
2 is to
matter.
the right.
Right.
Okay.
Don't think binary tree. Is this a heap?
Yes.
Yeah.
Nope. Here's
We thought it
9. What's its parent's value?
7.
Yeah, so what would have to happen? This 7 that starts percolating has to percolate as far as it can. Just like up here, when we had the 13, we had to percolate up as far as we could to make it a heap again. So this guy needs to go one more step and go 12, 6, 7, 4, 2, and whoop, 7 and 9 switched. So the 7's going to go there. Now is it a heap? The answer would be yes. Repeating that process, I'd move 12 out, move 7 back up. So basically what happened here, when I moved to 13, I moved it to this location and I said, don't touch that. Only think of that much. Only think of one less than the number of elements in the array. Okay, so let's go back to something right now. When we were building this here, and I had 1, 2, 3, 4, 5, 6, 7 numbers, how many times did I had to percolate down? Well, each time I added a number, I had to percolate down. Does that make sense?
Yes.
Yes. So I had to do 7 percolatings. Well, actually, excuse me, percolating up. I had to percolate up 7 times. Agreed? So as I filled this array in order to make it, excuse me, as I filled this binary tree in order to make it a heap, every time I added something, I had to possibly percolate up. Okay, so that was one way of filling the tree.
Why did 13 get replaced by 7 at the start?
Okay, so we were here, and you're talking about this one.
Yeah.
So what I'm leading into is we're going to eventually, and I'm thinking of the binary search or binary tree. Okay, and I want to be able. My goal is to use what's called a heap sort. Now, the idea of the heap sort is to take the largest, put it at the end. And again, we're conceptually thinking of it as a binary tree, but when we get ready to work on it, we're going to use an array. So when I get ready to sort this, all I have to do is look at this guy to sort. It's a faster way to sort the array. Okay, knowing that 13 is at the top, is in the first location, I'm going to move 13 to the end and move 7 up. So now I will have the array that looks like 7, 6, 12, 4, 2, 9, and 13. Now that 13 is gone, I only want to think of these numbers. So my new tree actually looks like this. And if I take care of this guy and percolate down so I can make it a heap again, then the largest will be on top. So according to this guy, 12 is now on top. 12 and whatever was at the bottom gets switched. Or here it is. 12 and 7 would get switched. So I would now move 7 up, have 6, 9, 4, 2, and the number 12 was moved to the end. So my new array that I want to 7, 6, 9, 4, 2, that 12 is at the end, one less than what 13 was. So now these are the numbers I'm looking at. And what I'm going to go through is once I move to 7 here, percolate down. However, percolate down is going to work, which we got the idea here. So it looks like I'm switching it with the largest. So it's going to be 9, 6, 7, 4, and 2. And when I take a look at this, I now have the array 9, 6, well, the 9's going to come off and go to that spot. So what am I left with when the 9 comes off after it moves here? Well, I'm actually going to switch what this time? 9 and so when I remove the 9 and put it in its proper spot, the last item is going to go up. So the 2 will go here, and I need to percolate down. So if I actually looked at the rest of these, I would have on the other end of this, the 9 or the 12 and the 13 would be in these blocks, array-wise. So that's what my actual heap sort is. It's taking the head, it's taking the first element in the array and moving it to a location of one less than what's left in my heap.
Okay.
I'm going to do another one in a minute. We'll come back to that in a second. Okay, so let's take a look at something else. Now, what if I just said my numbers again are 6, 9, 12, 4, 2, 13, and 7. I'm going to close a blind. Hold on one second. Does that make it easier to see? Yes, no, maybe. Can you hear me?
Yes, sir.
Can't hear me. Okay. So if I take a look at, can you hear me?
Mm-hmm.
Okay. So when we did this number a moment ago, we inserted 6, we inserted 9, and then we percolated up. We inserted 12 and we percolated up. And we kept percolating up over and over and over. Now that led to 7 percolates. We're going to take a look at something now that's going to eliminate some of those percolates. And here's what we're going to take a look at. I'm going to go ahead and fill the search tree, the binary tree, straight up. 6, 9, 12, 4, 2, 13, and 7. Now, as I mentioned a moment ago, we had 7 percolate ups, okay? Instead, here's what we're going to do. Instead of having 7, I'm going to fill the binary tree, and then I'm going to limit my number of percolates. Now, we could start here and say percolate, percolate, percolate. We could start up here and try to percolate, but we don't have to do that many percolates. All we need to do is start at the top of the first subtree, which is 12, which is 9, and which is 6, and do percolate downs. So instead of 7 percolate ups, what I can do is fill the binary tree and then start with the first parent from the bottom and do percolate downs, okay? Does 12 percolate down? Well, the answer would be yes, because it would need to switch with 13. So now I have 6, 9, 13, 4, 2, 12, and 7. Can keep going. Does the
Well-
9 need to percolate down? No?
No, it's
Okay.
already fine.
Does the 6 need to percolate down?
Yes.
Where would it go? To the 13? And then where?
Yeah.
So 6 is going to start percolating down. It's going to go to, we just said, to this spot. And remember, when we're percolating down, we have to go all the way. So can it go farther? The answer is yes. And now I end up with 13, 9, 6, 4, 2. That's a 12 because we switched them. 6 and 7. Is it a heap? First question is it complete? Yes. Second question is, are the parents greater than each of the children? The answer is yes.
Yeah.
How are we making out? So far, so good? All right. I'm going to take a binary. I'm going to take a tree. I'm going to fill it with numbers. I'm going to a little bit larger this time. 41, 33, 11, 16, 55, 27, 60, and 4. 1, 2, 3, 4, 5, 6, 7, 8. All right. What I want you to do is, first thing I want you to do is to make this a heap. Now, we had 2 ways. We learned about inserting a number, which I could insert at any time. And when I inserted it, I had to percolate up. Or if I want to get started with the heap, I can make it a binary tree, go to the parents, and percolate down. So let's go with the second way. I want to make this a binary tree, 41, 33, 11, 16. Again, I'm filling in from left to right. 55, 27, 60, and 4. Okay? My first question is, how many parents do I have?
3.
Nope.
Well, counting from 4.
I count 4, right? This 16 is also a parent. So there are 4 parents. So that means I need to do 4 percolate downs. Imagine if I would have tried to percolate up all of these when I added them in one at a time. I would have had 1, 2, 3, 4, 5, 6, 7, 8 percolates up versus 4 percolate down. So you see the advantage of what we're doing right now is called heapify. We're taking a binary tree and we're going to turn it into a heap. Once again, the way we turn it into a heap is we're going to take a look at 1, 2, 3, 4 parents. Go ahead. I want you to make this a heap, and we'll see if we all get the same ones. The numbers are 41, 33, 11, 16, 55, 27, 60, and 4. All right, my final answer was 60, 55, 41, 16, 33, 27, 11, and 4. Anybody get something different? Anybody need me to walk through it?
Actually, I would like to see a walk.
Okay. So the first number I needed to take a look at was the 16. So this location, then here, here, and here in that order. So when I look at the 16, I'm going to say, is it bigger than its children? And the answer is yes. So basically I have the same binary tree as I had a moment ago. The next location I look at is going to be here. Am I going to have to percolate down? Yes, because the 60 needs to be swapped with the 11. So after swapping those two, I move the 60 up and the 11. Once again, I'm only percolating down from this position. Next position is the 33. Yes, I need to percolate down. It needs to move to the largest. So the 55 moves up and the 33 moves to here. And then my fourth one was to check the head. And I say, yes, I need to percolate down. It's going to go here. So the 60 moves up and I check and it doesn't have to go any farther. So my tree is still complete and every parent is larger than every child. Does that help? This,
Faster.
say again?
That is definitely faster method.
Yes. Yes. The number of percolate downs is much faster than percolating up everybody. And you can see if I kept going with a larger and larger and larger list, my leaves could almost double what I have to do as far as the percolating. So I could be cutting it almost in half. What I mean by that is if I just looked at this 1, 2, 3, 4, 5, 6, 7 percolate versus if I would have had leaves here for everybody 1, 2, 3, 4, 5, 6, 7, 8, that would have been 15 versus that would have, if I would have had leaves all the way across, right, that would have been 7 percolate downs versus 15, the whole group of numbers percolating up. All right, so let's keep this tree in mind. And I have this 60, 55, 41, and so on. And if I looked at it as an array, 60, 55, 41, 16, I'm trying to get them all in here. I need to move everything over. 33, 27, 11, and 4. Okay, so I understand everything that's going on here, but to do this with linked lists would be extremely difficult because of the way I'd be moving a node at the head to the end and moving up and some of the percolates. It's going to be easier to do with an array setting. So what did we say? If I want to now sort this, I want to perform a heap sort. I have a heap and I want to use a heap sort. Okay, what did I say was going to happen? 60 is going to get moved to the end. So now I'm going to have 4, 55, 41, 16, 33, 27, 11, and 60. And as we talked about it before, what's now going to happen is my tree is going to be 4, 55, 41, 16, 33, 27, 11, and 60. Now, what I want to do is no longer think that the 60 is there. So this guy now sort of becomes invisible. This guy becomes invisible. So I don't need to know what the very end is here. I now need to know what is going to go here. But before I can move on, when I put this 4 at the top, I need to do what? Percolate down. I need to check its children. What's the largest child? Swap them. So the 55 is going up. The 4 is going to here. 27 and 11. Oh, no, wait, the 4 can even go farther. The 4 can be switched with the 33. It percolated down. And again, this 60 is kind of invisible to me. It's at the end of the array. So what's my array now look like? 55, 33, 41, 16, 4, 27, 11. What's going to get swapped? Well, I want to move the 55 to the end, to that spot, not the 60 spot. I'm done with him. So I want to move the 55 here, put the 11 up, and now I would have 11, 33, 41, 16, 4, 27, and 55. And we're now going to pretend 55 doesn't exist, and we're going to pretend that the 60 doesn't exist. Now that 11's at the top, what do I need to do? Percolate down. Looks like it's going to come this way. Okay, 41's going up, 33. The 11 moves to here, but it can still move down to that spot. 16, 4, 55 is already sorted, and 60 is already sorted. Now what am I going to do? Swap the 41 and the 11. 11 moves up, 41 goes here, 11 percolates down. 11 goes up to the top. Do you see, though, how this is working in the array? As I keep adding to the end, to that location, I'm slowly getting my list sorted in ascending order. Here's 33. Here's 27. Here's 16. 4. Here's 41. Here's 55. And here's 60. And again, these are sitting in my array protected, because I only want to deal with 1, 2, 3, 4, 5 elements of my array at this point. I don't want to touch 6, 7, and 8. So back to the array. When I was at 55, I switched it with 11. Okay, so 11 went up. And now how did I percolate down? Well, hopefully these are already written for me, but I would say 11. In the array, where are your children? We wrote those formulas down. 2n minus, or n minus 1 / 2 gave me, where do I have the numbers written? Remember the formulas you gave me? So if I'm at a parent, where are my children? Okay, 2n plus 1 and 2n plus 2. I check which one of those I may swap with. If I go to one of them, then I say, oh, check to see if I can swap with its children. So whatever number was calculated here, I'm going to use the 2n plus 2 and check its children. That way I can keep percolating down. Going in reverse, if I'm percolating up and I want to find the parent in the array, I would use this number, n minus 1 divided by 2, which would allow me to percolate up. So I'm using this visual of a binary search tree, even though I want to work with an array, and I want to work with those formulas to check locations in the array. Questions?
Actually, in regards to that parent finding question,
Yep,
should we?
I lost you. So if I did 0, 1, 2, 3, 4, 5, 6, and 7, and I have my formulas here, okay? And let's say I'm at location, the 27 is a 5, right? Where is this guy's parent?
Oh, I mean, it makes sense. It's at 2.
It's at 2. So 41 was the parent for 27. Here it is. 41's the parent for 27. So if I wanted to compare when I'm percolating up, I would say, okay, 5, your parent is 2. Do I need to switch? You know, and I would check it. And then I would go to this parent. What's your parent, my friend? And 41's parent is 0. So I would check, do I need to switch? And if I did, that's the idea of percolating up. Percolating down, right? 4, where are your children? Your children are at 1 and 2. Do I need to swap any? If so, I do it. Which one did I swap? Well, let's say I swapped at the second position. I need to keep going. Where are your children to see if we need to swap? It looks like 5 and 6. So this guy would check with 5. So 41's children are at 5 and 6. They're 27 and 11. Aha, do you like that? Dean said that's pretty cool. Other questions? So Vasily, do you understand what we're doing? I'm going to make everybody talk.
Sorry, what did you ask me?
Do you have any questions? Do you understand what we're doing?
We discussed percolating using both arrays and binary lists. It's all recorded. I have no other questions.
Brand, do you understand what we're doing?
Yeah, we're just like visualizing some
Okay.
like percolating algorithm done in the array, right?
Yeah. Kyle, do you get it?
Yeah.
Okay. Daniel, did you get it?
Yep, I'm all good.
All right. Maria, did you get it?
Yep.
BMAC, did you get it?
Yeah, I got it.
Okay. And Dean, do you understand what we were doing?
You kind of lost me, but I'll figure it out.
Okay. Two things. One, I'm going to try to save the video. Yesterday, I saved the long one and it didn't save right for me. So hopefully this one will save right. The other thing is in the NIOF book, you'll see the same kind of drawings, different numbers, and don't be afraid to look at that and go through. All right. This is big, you know, overall what we did today. So I don't have any, I'm not going to break you up and say write an algorithm for it and so on. But my question would, do you understand all the concepts of Heapify? And it seems like it's pretty good. So the 4 folks that didn't show up today, hopefully they're thankful that we're going to have a video and it'll help them out. So that's all that I have for today. Do you folks have anything else?